Okay, this is going to be lab number 7 on determining the Ksp of calcium hydroxide. So the first thing we should understand is what is Ksp. So Ksp is what we call the solubility product constant. Basically it tells you how soluble something is by taking the product meaning the multiplication of the cation and the anion, and of course Ksp, just like Kc, Ka, Kb, are all constants. Okay, so an example of what Ksp is if you have silver carbonate. Okay, and remember silver is plus, so you need 2 silvers to balance out with the carbonate that is 2 minus. Okay, and so if you take this solid and dissolve it in water, not much will dissolve, but a little bit will dissolve. And what is in solution is 2 Ag plus ions and 1 CO3 carbonate 2 minus anion. Okay, so really it is an equilibrium of what is the solid that's not dissolved and the 2 ions that are dissolved in solution. Okay, so the idea here is if you have Kc, you would calculate it as products over reactants. So you would have the silver times the carbonate divided by the silver carbonate solid. But because it is a solid, remember we said that because things are solid, its concentration is constant. So we're going to multiply it to the other side here. So we're going to multiply both sides. It cancels out on the bottom. And we get a constant times a constant. We're going to call this new constant the Ksp, or the solubility product constant. And remember, it is always equal to the cation times the anion. If this is the case, and this is what we're going to do in lab today, we're going to be taking calcium hydroxide, which is slightly soluble in water, and we're going to dissolve it as much as possible to make a saturated solution. Now, when we have a saturated solution, what we have in solution is the cation Ca2 plus and the anion OH minus, and there are 2 hydroxides because of the subscript 2 here. And remember, this is your cation and your anion. So Ksp should be calculated as cation times anion. This must be squared because of the stoichiometric coefficient of 2. Okay, so therefore Ksp is Ca2 plus times the concentration of OH minus squared. Okay, so now that we know how to calculate or how to set up Ksp, okay, what we're going to do in lab is we're going to make a saturated solution of the calcium hydroxide, and then we're going to titrate that solution, because titrating the solution will give us the concentration of OH minus and the concentration of Ca2 plus, which we're going to plug into our equation here to determine what is the Ksp for calcium hydroxide at room temperature. Okay, so the first thing that we're going to do is we're going to go ahead and make the solution. Once we've made the solution, we're going to titrate it 4 times, and this will allow us to calculate the Ksp. So I'm going to go ahead and move the camera. All right, so the first thing we're going to do is we are going to make a solution of calcium hydroxide. Okay, so I have weighed out here our 0.4 grams of calcium hydroxide. Okay, I have also got here 60 mils of DI water with my stir bar inside there. Okay, so what I'm going to do is I'm going to go ahead and I'm going to add this calcium hydroxide to my water. Okay, so now I've got my calcium hydroxide in water. Okay, you can't really see it because it's a white solid, but you can kind of see the white solid there. I'm going to go ahead and put it on the stir plate. I'm going to go ahead and get that stirring. And The idea is as much as will dissolve if I let it stir for a little bit. Okay, so I'm going to go ahead and get that stirring. Okay. And it looks pretty good. So I'm going to go ahead and pull it off the stir plate. And what I've got here is a funnel with a filter paper inside of it, paper clipped in so it doesn't slip. Okay. I'm going to go ahead and I'm going to pour the solution that I made, and I'm going to filter out any solid. And so you can see already at the bottom there's a little bit of solid that hasn't dissolved, right? Okay. Now that is a sign that I have a saturated solution inside there, because not all of it has dissolved, right? So really what is inside here, the liquid here, is the saturated solution, and inside here is Ca2+ and hydroxide OH-. So I'm going to let it settle a little bit. And I don't want the precipitate, I just want the saturated solution to titrate with. So I'm going to let it settle a bit, and then I'm just going to decant. Decant means to pour over the liquid and leave the solid behind. Okay, so that's exactly what I'm going to do. I'm going to decant. I'm going to try as much as possible to leave the solid behind, because I don't need it, and if I pour it over, it's going to clog up my filter. Okay. So I'm going to go ahead and gently just go ahead and pour that into my filter. And any solid that was in the solution is going to be left behind. Okay? And I'm not going to get a perfect, I'm going to leave a little bit behind. I really don't need 60 mils, so I'm just going to go ahead and let that drain through. Okay? Meanwhile, what I'm going to do is I've got here 4 Erlenmeyer flasks with a stir bar inside, and I have 4 of them because I need to titrate it 4 times. Okay, so to each of the Erlenmeyer flasks, I'm going to go ahead and add my 10 mils of water. Okay, so I've got 10 mils of water here in my graduated cylinder. Just going to add 10 mils here, and I'm going to do that 3 more times. Now the amount of water doesn't have to be exact, because really it's just to dilute the calcium hydroxide that I'm going to add to it, so that there is enough liquid in here so I can see the color change. A little more, a little less, doesn't really matter. And then I'm going to go ahead and take my indicator. Now in this lab, I'm not going to be using phenolphthalein. I'm going to be using bromomethyl blue. Okay, so I'm going to go ahead and add a couple of drops of indicator. Into each of my trial Erlenmeyer flasks. I'm going to add a little more to this one and a little bit more to this one. All right. So that looks like a nice blue color, I guess, from your perspective. Okay, so I'm going to go ahead and put this on the plate eventually. So this looks like it's doing a fair job draining. Okay, so I'm going to go ahead and start transferring or adding my 5 mils of the solution into each of my flasks. I'm going to meanwhile allow it to continue draining into a secondary flask. So if I need more, I have it. Okay, but really I do have probably enough to do at least a couple of trials. Okay, so I'm going to go ahead and take my solution. I've got my volumetric pipette here. Okay, and I'm going to take out 5 mils. Okay, it's important that you know exactly how much you're taking out, because the 5 mils is the It's going to be used for your molarity calculation later on. Okay? So I've got my, I'm gonna add, oops. So that's my 5 mils there. My 5 mils there. And last but not least, okay, so I've got 5 mils in every single flask. Okay, so now what I'm going to do is I'm going to go ahead and start titrating. Okay, and in the burette I have HCl. Okay, and I've got my stir bar stirring. Okay, and I'm just going to go ahead and slowly add my HCl. And I'm looking for a change in color. Okay, and the change in color should go from blue to yellow. It's like a yellowish greenish color. Okay, so I've got it adding dropwise, and we're looking for a color change. Okay, so right there you saw the color change. It was blue. Okay, now it's the kind of this yellowish color. Okay, looks like one of those Gatorade flavors. Okay, so I'm going to go ahead, and at this point what you should do is pull out your data table. If you don't have it, I would pause the video and pull out the data table. Okay, and you're going to write in your data table the volume of the HCl. Okay, so right now I have used up a grand total of 4 mils of HCl. So you should have a data table that looks like this. Okay, on your paper. So under the trial number 1, we're going to write 4 mils of HCl. And you're going to write 4.0 mils, 2 sig figs. Okay, we're going to take this off the plate, and we're going to do our next titration here. And again, I have my blue, and I'm going to continue to add my HCl. Normally when I do a titration, I don't add it this quickly, but I'm trying to save a little bit of time, so we're just going to go ahead and almost there. Okay, that looks good. Okay, and again, you can see it's a yellow color. Okay, so it has a yellowish color. Okay. And so at this point, we're gonna write again, pull out our data table, okay? And that took 3.8 mils. So you're gonna write down 3.8 mils on your table for trial 2, okay? For trial 3, Oh, almost there. Maybe one more drop. That looks good. Okay. And again, we're looking for this yellowish color, which you should see here. Okay. This is trial number 3, and that took up 3 points. Oh, not tall enough. Let me look at it again. So that's 11.6 subtract 7.8. So this is about 3.6 mils, getting slower and lower. Okay, maybe I overshot the first one, very, very possible. And do this last one fairly carefully so we get a fairly precise situation here. Okay, it looks fairly yellow to me. Okay. So I got here 4 mils exactly, 4.0 mils. Okay. So based on my 4 titrations, okay, you should have filled out on your data table, okay, the following data: 4 mils, 3.8 mils, 3.6 mils, and 4.0 mils. Okay. The next thing you really need to do is calculate the calcium hydroxide concentrations and then the OH minus concentrations, which will allow you to calculate Ksp. Okay. The way to do that, and we're going to go ahead and go look on our data table. Okay. For number 2A, okay, you're going to follow this roadmap here, where you have milliliters of HCl. Okay. And of course, for the first trial, you had 4.0, so you're going to put 4.0 right here, okay? So I'm going to put that in there for you. For the first trial, it should be 4.0 mils of HCl, okay? And you're going to convert from milliliters to liters using the metric system. 1,000 or 10 to the third milliliters is 1 liter, okay? And then from the molarity of the HCl, which we're titrating with in the burette, is 0.050 moles per 1 liter of HCl. And from our balanced equation, which is in the background reading, you have 1 mole of calcium hydroxide reacts with 2 moles of HCl. And then last but not least, for every 1 mole of calcium hydroxide, there is 1 mole of Ca2+. Okay? This will get you the moles of calcium hydroxide. Okay? Then in the next page, okay, it's 2A continue, they ask you to calculate the moles of the OH minus. So whatever answer you got from 2A, you're going to plug it here. Okay, so whatever you got from the previous calculation, you're going to plug it right here. Okay, and remember that for every 1 mole of Ca2 plus, there is actually 2 moles of OH minus in calcium hydroxide. This will get you the moles of OH minus. Moles of OH minus. Okay? So now from these two calculations, you have the moles of calcium 2 plus and the moles of OH minus. Okay? The last thing you need to do is calculate the molarity. Now remember, molarity is moles divided by liters. And remember, for every one of these Erlenmeyer flasks, I added with my volumetric pipette, I added with this 5 mils of each, right? So really, the volume is really 5 mils. So really, to calculate the molarity of OH minus and calcium 2 plus, all you need to do is take the moles of OH minus and the moles of calcium, which you got from 2A, so the previous problem, and you're going to divide it by the volume, and remember the volume needs to be in liters. So we're going to go 5 mils, because we took 5 mils out for each trial, okay? And we're going to go 1 liter, 10 to the third milliliters to convert it to liters. So 0.0050 liters. We're going to stick that here and here. And for each trial, of course, you're going to pull these numbers from 2A. Okay. Obviously, you need to do 2A not only for 4 mils, you need to do it with 3.8 mils, 3.4 mils, and 4.0 mils. So you got to do it for every single trial. Okay. Based upon this, okay, you now have the concentrations or the molarities of OH minus and Ca2 plus. The last thing you need to do is to calculate the Ksp. And remember, the Ksp is just the calcium times the hydroxide squared. Don't forget about the squared, okay? And that should go on the last column of your table there. And then take an average of your 4 trials. And remember, the average is just to take the Ksp of trial 1, 2, 3, and 4, add them up, and divide by 4, okay? With all of this information, make sure you go back and fill out your original table, okay, which is here. Okay, so make sure to go back and fill out your original table with your calcium hydroxide concentrations, your OH minus concentrations, as well as your Ksp values, 1 through 4, okay? Please make note of your average Ksp, because we will use that for lab number 8, which is the next lab, which we will do in person, okay? So that is a lab that we will do in person in the lab here at Gateway, okay? So now in terms of the post-lab, for the post-lab assignment, you will have to do a worksheet. The worksheet is in your lab manual. Do not write the lab discussion. You will not have to write a lab discussion for this lab. So do not, I repeat, do not write the lab discussion, okay? You just need to complete the worksheet, and then you are going to be able to submit the pre-lab and the data as one file to be graded on Canvas, and then you will also submit the post-lab, which is the worksheets, as one file on Canvas, okay? So that is it for this video on determining the Ksp of calcium hydroxide, lab 7.